created unprecedented momentum. So our vision is clear. It is to position India among the top 3 globally in semiconductor research, innovation, and workforce development by 2036. So this is not merely aspirational, but also achievable. However, if we have to realize this vision, it demands an unprecedented level of collaboration. We must dismantle the silos between defense research institutions, public sector undertakings, private industries, startups, and academia. We need to create seamless pathways for research translation into commercial products, foster deep tech entrepreneurship with patient capital funding, develop a world-class skilled workforce at all levels from technicians to PhDs, establish pilot-scale fabrication facilities which are accessible to academia and startups, enhance industry-academia partnerships with co-funding mechanism, and ensure IP localization and protection for Indian innovations. At DRDO, we are fully committed to this collaborative approach, and I can assure you that we will work with all of you to ensure that this vision is met. Coming to today's session, we have a very well-structured session to address all the points that I mentioned in my opening remarks. We will start with a keynote address by Dr. Bobby Mitra, who is the CIO and President of Tata Electronics, who will share insights on AI-first software-defined semiconductor and electronics manufacturing, a glimpse into future of intelligent manufacturing. Following this, we will hear from 3 distinguished speakers, Shri G.S. Madhusudan, founder and CEO of Infor and Semiconductors, Chennai, who will discuss creating a fabless semiconductor ecosystem in the country. Then we will have Professor Srinivasan Raghavan from ISC, who will present Vision 2047 for India's indigenous gallium nitride ecosystem. This will be followed by Dr. Suraj Rengarajan, Managing Director and Head Semiconductor Products Group, Applied Materials India, who will address the critical rise of advanced packaging technologies. We will then conclude with a panel discussion moderated by Professor Navakant Bhatt, Dean ISC Bangalore, joined by expert Srimati Suma Varghese, Director General Medcos DRDO, Professor Udyan Ganguly from IIT Bombay, and Shri Amitesh Kumar Sinha, CEO ISM MIT New Delhi, and Dr. Vibhu Sharma, Chief Technology Officer L&T Semiconductors and Technologies. This panel will also synthesize our discussions into actionable pathways forward. So with this brief opening remarks, I will hand over the session to Dr. Navakant Bhatt to continue. So we'll invite straight away Professor Mukta.
I think they have a movie that they wanted to play on the thematic.
Yes. Thank you, sir, for your motivating words and highlighting the kind of work we in DRDO doing for the nation to make it self-reliant. Thank you so much, sir. Ladies and gentlemen, as we explore deeper into the exciting realm of electronics and semiconductor manufacturing, let us briefly turn our attention to a special video presentation. This short thematic film highlights key initiatives, achievements, and vision driving progress in this vital field. Please.
India once imported its defense electronics. Today, we build them with pride, purpose, and power. Under Atmanirbhar Bharat, We're not just catching up, we're leading. Modern warfare isn't just about ammunition. It's about algorithms and electronics. From drones to satellites, tanks to submarine, electronics power every mission-critical system. India's homegrown capabilities are rising fast, with complex systems like Uttam Radar, Dharashakti EW, AEW&C, and the D4 counter-drone system now designed and built right here. At the heart of it all lies semiconductors, and India is moving towards self-reliance. DRDO's cutting-edge developments in gallium nitride, HEMTs, sensors and cryocoolers are setting the pace. From public sector giants to startups and MSMEs, a robust ecosystem is emerging. DRDO's partnerships, funding and hand-holding are creating a trusted value chain from chip to system. Initiatives such as DCPP Development cum Production Partnerships, TDF Technology Development Fund, TOT and DIACOE serve as backbone for development of futuristic niche technologies. And it's not just for India. We're exporting to the world, from surveillance radars for island nations to advanced avionics for friendly forces. The future battlefield is digital, shaped by AI warfare, quantum radars, directed energy weapons, and cognitive systems. India is building that future today. Technology leadership in defense electronics will secure India's sovereignty and drive us toward global leadership by 2047. Together we innovate, together we protect, together we lead. Building the future through electronics and semiconductor innovation, igniting the momentum of this journey into the future. The inaugural ESTIC 2025, the Emerging Science, Technology and Innovation Conclave. Imagine, innovate and inspire for Viksit Bharat 2047.
Team, this was indeed inspiring glimpse into Ministry's vision and initiatives driving India's growth in electronics and semiconductor manufacturing. To take the session forward, may I now invite Dr. Narendra Kumar Arya, Outstanding Scientist and Director ENIPR, to kindly introduce our Chairman Thematic Committee, Professor Navakant Bhatt.
I think we can skip that introduction in the interest of time.
One line. Good afternoon, everyone. Professor Navakant Bhatt is the Dean of the Interdisciplinary Science Division and a professor at the Center for Nanoscience and Engineering at the Indian Institute of Science, Bangalore. After earning his PhD from Stanford University, with that he continues. He has been chairman of a thematic committee, the main guiding force.
I think, there is a brief remark to be made by me for 4 minutes, but I'll just cut it to 1 minute in the interest of time. Just to continue on what the session chair, Dr. Kamath, mentioned, electronics and semiconductor forms the foundation of almost everything that we do today. But what is more interesting and sometimes also very challenging is semiconductors are driven by what is called Moore's law. Gordon Moore, who was the co-founder of the Intel, came up with this observation that every 2 years, the capability of your chip will double, the cost will come down, and higher performance, lower power, and so on and so forth. And now, of course, it's slowed down a little bit. Nonetheless, it's happening almost once a 3 years. So often people said Moore's law will die, but it has never, seen its death. And it's really going very, very fast and, very strong. So that presents a very, very unique challenge for us, because the technology changes at a breakneck speed. And if you want to be the leader, you have to continuously innovate, right? That is the very unique value proposition of this industry. And whether it is research, development, or manufacturing, we have to be agile. We have to be sort of aware of what's happening, and we need to really have a complete value chain from materials, equipment, and semiconductors, chips, and circuits, all the way to the systems, right? So that is why we have sort of curated this session where we cut across all these domains. And without much ado, I will stop here, and I think we will listen from the experts. Thank you.
Definitely, sir. This session will provide a deeper perspective on key initiatives, technological progress, and future roadmap in the area of electronics and semiconductor manufacturing. Now, may I request Dr. Meena Mishra, Outstanding Scientist, Director, Solid State and Physics Laboratory, to kindly introduce our keynote speaker, please.
Thank you. So our keynote speaker is Dr. Bobby Mitra. He is CIO and President of AI at Tata Electronics. He is responsible for driving AI first and smart manufacturing solutions across Fab, OSAT and EMS as well as broader enterprise. He also drives end-to-end agentic and digital twin for a wide range application from construction, safety, factory planning to supply chain and manufacturing operation. He has been in several key global leadership roles in Texas Instruments for over 3 decades, where he was a president and managing director of Texas Instruments India, and also led global smart manufacturing at TI worldwide. So now I invite Dr. Mitra for his talk. Thank you.
Good afternoon, everyone. Pleasure to be here, and thanks for inviting. The topic of my session is AI first, software-driven manufacturing. You will see a byline here, and that is really a once-in-a-generation opportunity, and I truly mean that. And through the course of the next 15 minutes or so, I'll really say why we really believe that it is once-in-a-generation opportunity for all of us. So the reason why AI-first software-driven manufacturing is a huge opportunity for us is threefold. Number one, it is because it really gets you to think completely different from a physical world. The physical world is really where all the construction is going on, the operations are happening, and so on. And that is where we are all used to manufacturing. And this is and the reason why AI-first manufacturing is so critical is because it turns that concept on the head, and it wants you to not just do AI in manufacturing, but you have to think of AI-first manufacturing. On the left of this picture, you will see the iceberg, right? Manufacturing has been there always, but what is happening now is manufacturing is very hot globally, and certainly in India. The CEO of the ISM is here, and you all know it is very, very strong in India and, of course, around the world. At the same time, the AI intensity is growing by the day. The confluence of this means that you have to look at it not like the picture on the left, which is traditional way. In the traditional way, people just look at the top of the iceberg. The problem is it is not sustainable. You solve some problems, you solve some silos, but it is really, really not the case because you cannot get sustainable results. To do that, and the reason for that is there are a lot of data silos. You can see below the iceberg, you can see a lot of data silos, a lot of fragmentation, and so on. How do you solve it? You go into an agentic world where it's like an ISRO, right? It's like the ISRO. You have the satellites and you have the control room that you see in the televisions. So you really manage all of these agents, this multi-agent framework through a central console. And these agents, what are these? These agents can be for maintenance, it can be for vision, it can be for scheduling, and so on. So it is completely a difference from a hardware-centric approach to a software-centric approach. It is actually a little more than that. Why are we trying to do that? What is the end vision? The end vision of this is autonomous system, and because you need to have a vision there, it is autonomous system. And by autonomous system, I mean everything that is in the factory what is in the factory? There's a lot of machines, there's a lot of equipment, there's WIP, material that is moving, right? All of us, several of you who have been in the manufacturing shop floor know what is the biggest nightmare of anyone working in a factory. What is the many problems, but what is the killer problem? Tool downtime, equipment downtime. Equipment downtime really kills the overall equipment efficiency, the OEE, as it is a critical factory metric. So you cannot afford that. It really kills everything. It kills your yield, it kills your top line, bottom line, and everything. The way to do that is autonomous. Autonomous means what? Suddenly the equipment becomes self-optimizing. It is self-maintaining. Usually when equipment is down, I said tool down is a nightmare for any factory. When the equipment is down, what happens? People just run to the factory, they open the chambers, fix it, trial and error, or whatever, deterministic or partially deterministic, and they fix it. But if the machine can really solve itself, that is really the self-optimizing, self-maintaining, self-aware. Machines suddenly become self-aware. So that is the advantage of going on the right, the confluence of AI first and manufacturing, which I call the software-defined manufacturing. There are many opportunities when you go from the left to the right, when you turn the thought on your head and conceive of things from the AI first and the software world. What are some of these? For example, your construction is going on. I mean, as you know, in Tata Electronics, we are building India's first fab and our indigenous OSAT. While the construction is going on, if someone wants to see, I want to see the factory. The factory may take some months, some period of time. I can show the factory today digitally. Again, not using animation, nice videos, no. Using simulation. Simulation is very powerful. In this AI first world, simulation is very powerful. The beauty is simulation is also very forgiving because you can do hundreds and thousands of iterations before converging on one, and then you go into the physical world. That's what I mean by thinking AI first, with all the aids like simulation, all the aids like physics, chemistry, because it's a combination of data and science, right? So all of these combinations you can use to do lots of simulation. So that's in construction. There's several other areas that I will talk about, but again, I just want to say that it is not AI in manufacturing, it is AI first manufacturing. It's a conceptual change in the thinking. Let me go one level deeper. These are some examples. For all of you who have worked in any manufacturing, doesn't have to be semiconductor electronics, can be automotive, could be a chocolate factory, whatever it is. What is the basic unit? What is the basic thing that runs the factory? Is the MES system, right? Manufacturing execution system. That's the mother of all the data that is there in the factory, MES. Then PLM, product lifecycle management, that takes the data up and down the stack. And then, of course, the ERP, which has all the financial data, inventory data, and all that. So this triangle is very important in any manufacturing. MES, PLM, ERP. Often you call the top floor to shop floor because data of the customer demand is coming from the ERP. The factory data is coming from MES upward. So that triangle is very important. That triangle is getting completely reimagined in this AI first world. Vision. Vision is probably one of the most important things in any manufacturing facility, for sure, in electronics and semiconductor. What is unique about electronics semiconductor? It is data, terabytes, petabytes, and zettabytes of data. It's a huge amount of data. And data is not, you talk about this multimodal these days. This is not even multimodal. It is high frequency data, not only different types of data, but different classes of data. Data is not coming at 1 hertz, data is coming at kilohertz. So it's a very complex thing. So in the vision world, all of us have studied computer vision sometime in our colleges. But in AI world, while all of us know about LLMs and so on, there's VLM, Vision Language Model. The beauty of vision language model is you can give it a YouTube video or whatever, it can bring out the captions, it can kind of come out with the gist, and you can query it just like you query any text. So that can be very powerful, and it can come up with a lot of insights and actions from there. So vision, which is really part of, for example, in any factory, good parts and bad parts really are determined by earlier inspection in the manual world, but now AI-driven vision. Scheduling. What is scheduling? I mean, all of us, again, going back to college, have studied OR, right? Operations research. I mean, that is probably one of the most important determinant of cycle time of any factory. Any factory metric, I mean, cycle time is one of the top 3 metrics, right? Cycle time of the factory, throughput of the factory. And how does it depend? It is really the scheduling. What is scheduling and why scheduling? Because factories, the material movement is really linear. How many linear factories have you seen? Semiconductor? What is unique about semiconductor manufacturing? I mean, I know several of you here in the audience have worked in semiconductor manufacturing. Uniqueness of a semiconductor manufacturing line is a very complex phenomena which is called re-entrant flow. So when the material is going, it is not going here, it is not even forking out and coming back. It is going back and back and back, going back. So any material goes through equipment multiple times at different stages of the world. So this re-entrant flow makes OR very complex, and that's why you need AI-based scheduling of the factory. Manufacturing layout, again, an area, and I'm trying to make it real by giving some of these instances. I mean, suppose there is a factory, customer demands change, right? Fluctuate. I mean, gone are the days where you have high volume and low mix. Especially in Indian context, you have different types of products, some with high volume, some with mid volume, some with low volume, and that's fine. Our factories have to adapt to this high mix environment. High mix is very hard. High mix manufacturing, high mix mid volume manufacturing is very hard. And to your rescue is AI, because now you cannot have a fixed layout factory. You have to have flexible factory. It's a very important concept, very difficult, but very important concept. You have to have reconfigurable factory, and that's what we are trying to do. Reconfigurable factory means what? I can have a different aspect ratio of the equipment, different number and types of equipment, and so on and so forth. So these are very important concepts and again, the beauty of it is, again, remember, software defined. You can do all of these in simulation, and then you can decide how to reconfigure the factory. And maintenance, again, can be done a lot through AI. I've given some pictures on the right of some of these concepts. I will talk about one or two. On the top are some of the equipment from a semiconductor manufacturing. And what you see on the top of the picture on the right are 3 words. And one of those words is often less used, but it is very important. People talk about digital AI, agentic AI, but they miss one thing, which is physical AI. The world that we are going in is a combination of digital AI or agentic AI and physical AI. What is the phenomena that characterizes physical AI? Actuation. We have all studied, again, back in school, sense process control, right? Which is really sensing and control loop. But the actuation is very important. You have to combine sense, control, and actuate. That loop is very important, and that loop happens through things like robotics and such other. So, for example, any equipment in a manufacturing flow is giving out hundreds. One equipment can give out hundreds and thousands of sensors, which is essentially telling the health of that equipment. But also, in the autonomous world, you also have to send signals back to the equipment so that the equipment can reconfigure itself and optimize itself. So that's the type of thing that we want. The picture in the middle talks about the reconfigurable factory. You can see the red dots. It tells do not put an equipment in those, and you can reconfigure those in many order. Each of those small yellow dots are the different equipment if you zoom into those. In the bottom, you will see the maintenance. You can see any in a chillers, boilers, or any clean room equipment. You have all the data at a click. You can do whatever. Again, those are some examples, pictures I took to show a software-defined factory. One final level of detail on the how. Everything I said was the what. And to see, this is an important picture that gives you a glimpse of how you do this loop of sense, control, and actuation. You have to read this picture from the bottom. At the very bottom is all the data in any semiconductor electronics manufacturing, and the type of data, the velocity of the data, the variety of the data is immense. And you can see some of those written here: equipment data, the MES data, the material control systems data, and so on, video and image data. So you have all of the data. So that's the core data. But there's a word to the left which is extremely important, and that is ontology. Ontology really helps you. Data ontology is extremely important in the AI world because it helps you contextualize the data, standardize the data. Because if you just take the data and try to get intelligence, you will not get good results there. You will get a lot of hallucination. So data ontology, context engineering, which is a word you will hear a lot in the AI world today, are very important. So you have to use the right data ontology here. But then you go to the most important layer, which is in the middle, which is what I call the connected digital twin. There are three types of digital twin. One is the equipment, all the equipment in the manufacturing floor. And I want to get people in the manufacturing floor in the AI world want to get, for example, there is a etch machine, there's a diffusion machine in a semiconductor world, or similarly in electronics manufacturing, CNC machines, injection molders, and so on. I mean, you cannot think of those as black box in today's age. You have to get full visibility of the physics and chemistry and the science that is going on inside those. That is happening through the equipment digital twin. I should be able to visualize everything and understand the equipment. The second part is, of course, the operations digital twin, cost, real-time information of the operations and cost and then the supply chain, which gives the outer world. So really structuring all the raw data at the bottom, of course, through the ontology into all this multimodal learning with this three connected thing. If you get these two bottom parts right, the third part, which is really magical in the AI first manufacturing, can start making shape. What is unique about the top part? You have all heard data science, dashboard. I get beautiful big screen showing all the yield data, all the factory state of each of the equipment, whether it's up or down. That is yesterday world. In the tomorrow world, just getting insights, not enough. You have to get the insights, but also the action. You can see some of the questions. I mean, I should be able to say, in the AI first manufacturing, I know my cycle time is poor. Do I have to really go through the thousands of data to understand? You should be able to get, if you go through bottom to up, you should be able to query the system, and all the data up through the digital twin should be able to not only answer, but also correct itself. So that's what we are trying to do in this AI first manufacturing. And if you want to do root cause analysis, it's a very difficult thing, it takes a lot of time, so you can do this in this AI first world. So just to summarize, it's a paradigm shift to really look at it at AI not as sprinkled all over, but is embedded in the entire stack. It has to be embedded in the entire stack. It has to be conceived like that. That bidirectional process control and actuation, don't think of sensors only. Then you are not getting into the autonomous mode. You have to send the signals back to where it came from so that you can make it self-optimized. And finally, you really have to do self-optimizing factories with human feedback, because at the end of the day, autonomous sounds great, but you have to have once you have really narrowed down the choices, you have to have the human feedback as part of the autonomous operation. So with that, I conclude my talk and happy to take any questions later. Do we have questions now or later?
I think we have time for a couple of questions. So please raise your hand and please introduce yourself before asking.
My question is that you emphasize the need of AI-based simulations. So that is very important. In fact, two approaches are going on. One is physics-informed neural network, that is phase-based simulation, and another is data-driven, which is physics agnostic. So what is your comment, merits of demerits of these two approaches?
Yeah, the answer is, it's a great question, and the answer is in the question. It is, people think data is gold, data is oil, absolutely true. But if you really want to get to the real information from the data, it has to be data plus physics. You have to get the data out. It's like the plus in the control, in the process control, right? The data has to come in, you have to bring the physics of it, and then go back to the control room. So absolutely, to get a real good data, it has to be physics. You can call it science, physics, chemistry, whatever. The physics aware, data aware, but embed data, the data on top, because data, beauty of data, it gives, physics is how it should perform. It is the golden truth, right? Physics is never wrong. Physics is physics. Data is the current state. So that combination of physics and data is very critical. Yeah, yeah, that is a question there. Maybe just wait for the.
Thank you. I'm Vaibhav, a Bitsvilani alumnus,
Yes,
and from someone who has been used to seeing the physical workshops and the manufacturing floor, when we are talking about AI and all, so are the physical machines still gonna be there? And what all, I mean, what all is happening before that leads to that physical machine later on?
No, I hope I didn't give a thing that software defined means you have to think software first, digital first, AI first. But the beauty of it is, what I said is, of course, physical equipment will never go away. That's running the factory. Real equipment, real output comes out of real factories. So that's the simple answer. But you can do a lot of iterations in the software world. Okay. Yes, you got your mic back. I can hear you, though. I will repeat the question. Yeah, yeah.
So my question is that around 2022, there was a report that now for the advanced node, especially 5 nanometer and smaller, the verification and validation part is taken over the actual cost. It's almost like 90% and over. So, beautiful picture about your digital twin and where that validation part is coming in.
See, you're right. As chips are getting this, there's a question that goes from manufacturing back into the front end, the design part. So, question is, when you go back into the front end, which is where the design is, verification validation is becoming a very important one. That is absolutely correct. And that will continue as chips become more and more complex at the sub 10 nanometer. It is absolutely going to continue. Some of the solutions that are happening in the AI world, verification is probably one of the first areas that will be attacked by AI. No question. Can it be solved and will it be a no-brainer? No, it has to be done very appropriately. Probably the biggest productivity improvement, and this is a question beyond manufacturing in the design world, will come from the verification. For the others who have not, validation is really when the silicon comes back, then you have to validate it. So this verification is before silicon, validation is after the silicon comes back, and you make sure it is. So both of these, I think AI has a big role to play. So while the complexity will go up, I think you have a great ammunition in AI in the verification validation.
So in the interest of time, we will take the questions later during the tea break. So please give Dr. Mitra a big hand.
Thank you so much, sir, for that truly enlightening and thought-provoking address. Your insight on AI first and its different aspects in manufacturing has given us a powerful perspective on the future of this technology, and also we are little assured that this physical will never be obsolete. Thank you so much, sir. Now we move to our next part of the session. May I request Dr. Ramakrishna, Associate Director, ARCI, to kindly introduce our first session speaker.
I'm privileged to be here and introduce the next speaker of the session, Sri G.S. Madhusudan. As the founder and CEO of Incore Semiconductors, India's first ever processor IP company, Sri Madhusudan is leading the charge to create self-reliant chip industry in India, and he has laid the strong foundational work in managing the Shakti processor project at IIT Madras for over 9 years, and with his vast experience, he has mentored a lot of startups in the country, and he has also managed R&D for diverse hardware and software products development in the country, and he has been a very important member of several government bodies, including India's AI task force and National Policy on Critical Technologies. With this brief introduction, I request Sri G.S. Madhusudan please to deliver a lecture, please. You are please welcome, sir.
So I'm going to talk briefly today about creating a fabulous semicon ecosystem. Now, why does this matter? See, you've probably been hearing a lot of 60,000 foot presentations on deep tech, semiconductor, a lot of jargon. You hear a bunch of things. You go out of the conference, it all goes out of your head. So today I've made sure, one, no pretty pictures at all. Simple words, simple facts that you can take away and you can challenge me offline, right? This is hard data, actual plans of what needs to get done, and it's almost like a doctor's prescription, correct? The prescription may be wrong. The patient could potentially die. Some doctors do that also. But this is my view on how things should be. I'm going to address the issues facing this sector and the nature out of areas of concern and the nature of support needed. One key thing you should remember when we talk chips, most of the money is made by the IP providers and the design people. NVIDIA does not do manufacturing, but it's a 5 trillion, whatever, put whatever number of zeros you want. All the manufacturing is done by TSMC, the packaging is done by other people. Out of a total, they make 5 to 10% of the money. The maximum money is made by NVIDIA. A good chunk of that comes into my family because I think we got like about 15 people working in NVIDIA. So, no, Inco doesn't make that kind of money. Look, till now we had a problem. A semiconductor industry will never happen unless you consume locally. You cannot create a semiconductor ecosystem just by exporting your way out. Taiwan and a few countries did it on a small scale. China arose because it manufactured a lot for local consumption. The final products get exported, but those semicon parts get used locally. The people who get criticized the most, the EMS manufacturer, you will never hear anything pleasant being said about the EMS people saying they make 2%, 3%, it's not great technology. That might well be true, but they have laid the foundation for the parts that you see. Even completely imported technology, which is 100% imported, you pay royalty, all of that, that is manufactured out of Noida, that is manufactured out of Chennai, correct? So unless you have that base, suppose I make a piece of semiconductor, who do I sell it to? As a fabulous startup sitting out of Bangalore or Chennai, I can't go sell in China. But if Foxconn is manufacturing in Chennai, I can go to the Foxconn factory and say that, look, this is your bill of materials. You got 200 components in there. You tell me which of these components you're willing to buy from an Indian vendor. So the unsung heroes of this semiconductor revolution is the people who are at the bottom of the food chain, who don't get a credit. They have laid the foundation for all of these things that you see. These are manufactured in India. Now the fabless ecosystem has got something to sell into. So without this EMS ecosystem, this semicon revolution cannot happen. So it's clear there's enough demand. It's about $30 to $50 billion US dollar now, and it's projected to rise about 100 billion USD in 2030. This is just India alone. Strategically, we'll be importing more semiconductors than oil. And the demand is even more for modules and solutions, so it's how you package and sell it. So tactical and strategic priorities. There needs to be two sets of priorities, right? Strategic priorities for the long run, but tactical also. Look, 100% import is neither desirable nor sustainable. Everybody agrees on that, right? But to create a semiconductor product ecosystem, you need fabless companies, you need design services companies, you need IP companies, you need chip foundries, you need packaging guys, you need semiconductor equipment manufacturers, which everybody forgets about. For some reason, everybody talks about everything in the chain, but that entire equipment is imported. You know who are the two major suppliers of equipment? It's either the Americans and now the Chinese. And crucially, and probably everybody in the government is going to vilify me for saying that, we will probably be forced to buy more Chinese semiconductor equipment than the US over a period of time, because the Chinese stuff is going to be dirt cheap. If you want cheap semiconductors, it has to be done with cheap equipment. And guess where the cheap equipment comes from? It doesn't come from ASML or KLA or somebody, right? It will come from the Chinese. So it's going to be an interesting battle. And we don't want to get stuck importing equipment. So the Tamil Nadu government, for example, has a semiconductor equipment research park, right? And see, the Tamil Nadu government couldn't get the fabs. All went to Gujarat, fine. So they said the next best thing is we'll manufacture the equipment, right? So Coimbatore now has an equipment research park, and they've already started equipping. India is now actually exporting semiconductor equipment as of, I think, June of this year. The first piece of equipment got shipped somewhere in May to June, right? And of course, CAD software. 3 companies control the entire software tool chain: Cadence, Synopsys, Mentor Graphics, which is now Siemens. Which means, if President Trump wants an embargo, it takes him all of 5 minutes to shut Bangalore, Chennai and Hyderabad. That is all it takes. Cadence switches off the power, all the 20% design engineers that we are talking about are going to be idle. And then what do? You go drive Uber and Ola or whatever, right? That is the power the rest of the world holds over us. Strategically, we are not there yet. So this is the broad. But it is also important to decide what strategic things you're going to do and what tactical you're going to do, right? Tactical is important. See, the ideal mix is 85% tactical, 15% strategic. So tactical priorities, fabless, IP, design service all fall into that, okay? Design services, been there, done that. Design services is basically an Indian thing. You don't have to worry about it. It's a done deal. IP is kind of getting there. I just found out that there's actually a company out of Noida that is selling advanced A2D converters into China. For all you know, Chinese defense equipment is using Indian IP. And it's not a joke. 2019, I was invited by the PLA to give a keynote speak in Beijing and Wuhan. Wuhan on December 19th, 2019, the week that COVID broke. I was supposed to give a talk in Wuhan. Fortunately, I couldn't make the flight. I went to think. In 2019, the Chinese did not have a major RISC-V program. They were thinking about either licensing the Indian Shakti program or the Berkeley one. They did the Berkeley one. We were 5 years ahead. Come 2025, they're like about 10 years ahead of us. Correct? So, in tactical priorities, the first priority should be nurture fabless and IP companies, because ultimately the intellectual property matters. Everything else, like I said, is 15%. Correct? Why? Because IP and design product companies take away most of the margins. That is where the money is. Like if you ask a bank robber, he'll tell you, why do you rob banks? Because that's where the money is, right? So max forex reduction will happen with the localization of these two areas. I know I'm going to get hammered tomorrow for saying this. The fabs and the OSATs do matter, but they are strategic priorities. The Tata fab is going to come in 2028 or so, but I am starting to manufacture chips starting this month, right? So I don't mind using TSMC. I don't mind using UMC till the Tata fab and the other fabs comes up, because I got to make those margins, correct? Design service in India, like I said, is very mature, does not need government intervention. It needs business. So our focus should be on fabless and IP companies. So fabless, okay, this is the key thing, right? And in the lower end of the market, talking below $5, innovation is not needed. Okay, we need to ship products. We need to ship standard products. How do you do that? A simple analysis will show that in the sub 5 US dollar, what do we do? Passive semicon, right? MOSFETs, IGBTs. Everybody ignores transistors and resistors and diodes. till Nexperia says, I won't ship to Europe, European auto manufacturing comes to a grinding halt, NVIDIA will still supply to everybody, right? But the little diode that you have in the power transistor is gone. So the Chinese literally have everybody by the throat because the diode is going to be 1 cent, half a cent. You cannot manufacture it cost effective in any other place other than 2 countries, India, China, right? So those matters. BLDC controllers, especially fans. India is the largest consumer of ceiling fans in the world. Nobody else buys ceiling fans like we do. Each manufacturer probably does like about 10 lakhs, 20 lakhs a month, right? Each one of the ceiling fans, because it's an energy effective fan, uses a BLDC controller, uses a processor. Now the Atomberg fans have got a thing. Every fan has got 2 CPUs. Every fan needs embedded software. So every fan potentially could now have a software bug. So somebody hacks your fan, instead of going this way, it can go that way. No, it's a great way of spoiling somebody's sleep, right? If you keep rotating the fan back and forth, the poor chap doesn't get good sleep. Power management controllers, right? All of you are, your mobile phone is not there, you're dead. So all of us spend half our life looking for a mobile phone charger. Correct? All of those are there. And we are one of the largest manufacturers in the world, by the way, right? Wi-Fi, Bluetooth and RF controllers. Again, all your headsets, every one of you I'm pretty sure has got something that you pop into your thing and that is a Bluetooth headset, right? IP camera controllers, application processors, all the standard stuff to see. These are all standard items and every one of these is below $3 in price. I have what I call a 20-20 vision, now it's become 25-25, now it's become a 30-30 vision. The vision is very simple. 30% of all parts costing below $30 should be designed and manufactured out of India. It's as simple as that. You want a concrete vision for semiconductors in India, any part costing below 30 parts, anywhere in the world, 1/3 of that should come from India. You put a timeline on that, 2030 obviously can't happen, but at least by 2035, and it can be done. There are only 2 countries in the world capable of manufacturing low-cost semiconductors, India and China. The rest of the world simply does not matter. You simply can't. The cost structure is so bad that we are the only 2 people who can manufacture at reasonable profit margins. So what's the key issue facing the fabless IP space? Funding, talent, IP cost, fab cost, CAD software cost and market access. The CAD software has done, MeitY and DST have done a wonderful job. They have removed all the standard excuses that Indians are capable of giving. Software is too expensive, okay, free. IP is too expensive for this, okay, we'll do that, right? So every excuse that a typical startup can give, MeitY has got rid of that, right? So we now have no excuse left. But so what is the problem? We still have a problem. See, ultimately MeitY and DST can bring you the food. They can even put that food into your mouth, but you still have to swallow it. That is right. See, for a nascent concern, this is the problem, right? Funding is still a problem. But more importantly, what needs to happen is the government needs to focus on some of these. Take like 4 or 5. I think Daylight 2 is supposed to handle that. We need to have very concrete mandates of local procurement of these parts, right? The instant you do that, automatically the demand side is taken care of and the venture capitalists will fund the companies. The government doesn't have to spend money, right? The government has to do demand creation of these parts. You don't have to worry about any of those parts. The parts that you see there, these parts actually drive the semiconductor revolution that you see. 80% of the semiconductors that you encounter other than the major PC or mobile phone processor are all these parts that you see over there. It's amazing that just simple 10 categories control everything in the industry. It's not difficult. And by the way, the intellectual property for all of that, except perhaps H.264, actually even that is available, right? All IP is available in India, design talent is available in India. All of these are either getting manufactured or will be. It is just a matter of demand creation. But by 2027, every one of these can become 100% local. So what is the support needed? There is still some critical IP, especially in video and others, that is still not available in India. It is important that MeitY creates a IP database and provides that at low cost to Indian companies. Encore, for example, my own company, we give our IP free of cost to startups for their evaluation with some nominal charge for support and stuff, and you pay us when you go to production, right? We need similar things for other IP also. We need subsidized shuttles. The maximum cost that a startup has to bear is the cost of fabrication, because in chip design, manufacture, I mean, ultimately TSMC takes away all the money, right? So they deserve the money, I'm not blaming them, but somebody needs to support it by a subsidized shuttle, right? And far more importantly, we need government localization mandate for demand creation and enabling VC investment. The government does not need to put in money, but it needs to ensure that the parts designed in India are consumed in India, right? And MOD till today does not have a official mandate, and we are trying to see how we can get that across, because whenever I talk to the defense major, they're saying, look, we can design the parts, we can put it in there, it is even cost effective, but unless there is a mandate, why should I do, right? So Operation Sindoor, we've all talked about all the radars and stuff. All our radars, all our critical systems run on American chips, the big ones. So very interestingly, all the big chips in the world are manufactured only in US. Europe does not have a single big chip vendor. Europe does a lot of smaller chips, some automotive chips and stuff. But if you look at PCs, Intel, AMD, right? If you look at laptops, Intel, AMD, NVIDIA, all of those people, right? If you take mobile phones, Qualcomm. Yes, there is one called, there's MediaTek in Taiwan, right? You will find the odd exception. But pretty much any chip costing more than like $50 comes from the US, right? So it's a very critical part of our infrastructure that we're so reliant on not just one country, but just like 6 companies. So we need to get that, right? We need an enhanced PLI once we start manufacturing for at least 5 years. So there is one suggestion that I like to make. This is what the Chinese did, right? Look, we need fabulous startups, but we need more manufacturing startups. So if I take 5 standard parts, let's say smart cards, electricity meter, they're like, why can't the government essentially commission CDAC to design 5 chips? Let the startups not do the design. That design can be given free of cost to startups to do the manufacturing. Because the biggest problem is, if I as a startup design a chip, take it to the market, I am new, the customer may not want to trust me. So if you go buy a Wi-Fi or a Bluetooth module from China, you buy 100 different modules, you will find only 2 designs. So what the Chinese government has done is, it has asked 2 companies to do 2 designs. Those 2 designs are distributed free of cost to multiple vendors who then manufacture it, right? So they kind of do like contract manufacturing, they do. I'm done. So I think we need to try something along those directions, not permanently, but what I would like to see is by 2028, India should be supplying at least 100 million parts every year to the local market, right? So as an initial measure, if we can pre-design some components and seed the market, then our startups will start shipping parts. This is very, very key, right? Ultimately, any program has to be measured using quantitative metrics. We can all talk till the cows come home, but in the fabulous space, only one metric matters. X million parts shipping by a target date, nothing else matters. So if we say 2028, if we say 100 million parts to be shipped, obviously GST also gets paid, it's very easy to measure that, right? Once you reach the volume, then a lot of other strategic things can happen, but the tactical stuff needs to happen on very quantitative basis. So in conclusion, it's key that we have concrete measurable goals for the fabulous ecosystem. Otherwise, the government will give a lot of subsidy support and all that, and we can't measure whether we succeeded or not. Focus and tailor-made support is must if you have to meet these goals. And this is what I keep telling my counterparts in the government, right? For 100 years, we've been telling the government should stay out of the private sector. You guys need to get out. We need to do it, right? For once, I am begging you, please intervene, okay? Not permanently, but at least for the next 5 years. Because every semiconductor ecosystem that has come up anywhere in the world had a very strong government hand, including the US. Let them not preach the virtues of capitalism to you, because they were 100% socialist when their semiconductor ecosystem started. And once they succeeded and they're thrown off the government, look at how much funding Intel gets to. Intel to get salvaged, the US government had to fund what, 5 billion, 10 billion? When the US auto industry almost collapsed after COVID and stuff, the US government had to intervene, right? So everybody wants capitalism till their balance sheets are running in the red, then they'll go running to Papa, right? So with that I conclude.
I think we have time for a couple of questions. Yeah, please.
I think it needs a mic. Oh, that's okay, I can hear.
Anusandhan National Research Foundation.
Okay.
You talked about the India's fabulous semiconductor strategy. So I want to ask, are there some policy and institutional framework by the government of India already in place in form of some missions or some program launched or some kind of partnership with different institutions?
No, the government has done a
So
wonderful...
can you just give some detail about those?
Yeah, the government has got two programs called C2S and DLI from MeitY. DST has got a program. In fact, we are getting a DST funding for the research project. DRDO also has got an excellent program through TDF. Look, there is more than enough government funding. In fact, we probably have more funding than can be consumed by the private sector. Okay. So I was once talking to the MeitY secretary. He said, look, I said, what is the thing? He said, Madhu, I don't want any private sector company to say that I failed because of lack of funding, right? I don't care if 90% fail, but if 10% succeed, that is enough. That's how the industry works. What is needed is just a little more focus on, say, 5 parts. See, ultimately, what do we have now? Our problem is not technology. Our problem is a crisis of confidence. Nobody believes in an India-made chip. You will start believing it when you have a mobile phone and you open it up and you see 4 India-made parts, right? Then you will start believing it. So I am simply talking about a tactical approach and how we can take 5 separate parts and get them into a volume of 100 million pieces by 2028. It's a simple tactical approach. Yeah. Yes, sir. Yep. Please go ahead. Sir.
Yeah, so my question is that what you said that the equipment is a main part of the fabrication. Even if you go for the low cost chip fabrication, so the development of quality equipment is very much necessary. So what the thrust is given for that area?
You're talking about semiconductor equipment, right?
Yeah. Like the deposition or ion implantation and...
I'm not aware of any major government policy over there. I think the focus has been more on getting the fabs up and running. Bobby can probably comment more on that. He comes from a fab company. I know the Tamil Nadu government has a policy because I'm an advisor to them, and Rajamanikam of IVP is advising them on that, and there is a semiconductor equipment park, there are benefits. But at a MeitY level, I have not seen anything public on equipment manufacturing. I don't come from that side, I come from the fabless side. So please don't take my opinion as gospel, because I'm pretty sure after this call somebody will ring up saying, we have a policy, why did you talk about it, right? I am unaware of it because it's not my area of expertise. But if there isn't, there should be. If there is and I'm not aware of it, then probably we need to publicize it more. I think 2 questions.
Yeah, last question.
Thank you for kind of giving a very straightforward scenario or like condition or state how we'll do. Certainly design in India and fabricated in India chips may take some time. I was curious about knowing, as you said, IGBTs and diodes and MOSFETs, discrete components. Yeah. What is the status of that kind of in India, whether we are fabricating, exporting, importing?
We were actually fabricating and possibly exporting in the 1970s and 80s.
Okay.
Till 90s. Then we stopped. Now we are starting to do it again. 2 companies are in the forefront, IVP and CDIL. Okay. We will get there. That's not a problem. Very high-end stuff. I mean, HEMTs are done by DRDO and all of that. Okay, ultimately for food security, what did we do? We did gehu and chawal. So semiconductor should start with MOSFETs and IGBTs and diodes. Okay, the NVIDIAs and all that can wait.
Certainly.
कोई जरूरत नहीं है.
Thank you. Thank you, sir.
Sure.
I think he deserves a much bigger hand than what the audience.
Yes, yes. So thank you so much, sir, for that insightful talk. I would rather say that insightful prescription. And need of our is to work for basic needs, things which we can produce. So to continue the session, may I now request Dr. Suchita, scientist DST, to kindly introduce our next section speaker.
Good afternoon, ladies and gentlemen. It's my privilege to introduce our next speaker, Professor Srinivasan Raghavan. Professor Raghavan is a distinguished speaker, a distinguished material engineer, and a professor at the Center for Nanoscience and Engineering at the Indian Institute of Science, Bangalore. A metallurgist by training, His work bridges the gap between material science and cutting-edge electronic devices. For the past 2 decades, Professor Raghavan has been a central figure in a multidisciplinary team at IISc that successfully developed India's indigenous gallium nitride devices. His most significant contribution is leading the translation of his research into practice. He is the principal investigator of the Gallium Nitride Ecosystem Enabling Center and Incubator, a facility funded by MITI to enable low-volume production of gallium nitride devices. Demonstrating his commitment to commercialization, Professor Raghavan has founded Agnet Semiconductors, India's first private company to manufacture gallium nitride devices. In recognition of his pioneer work, he has been honored as a fellow of the Indian National Academy of Engineering and is a recipient of the prestigious Dr. Abdul Kalam Technology Innovation National Fellowship. Over to you, sir. Thank you.
Okay. So, thank you. Okay, after that entertaining talk, I have big shoes to step into. I thought a designer would have good pictures, but then you're a boring semiconductor designer. Maybe you only have circuit diagrams or layouts. So we'll go from design to manufacturing. And this is gallium nitride manufacturing, and we do manufacturing with actual physical machines. These are not virtual ones. You can do without them. We all know that the gorilla in the room is silicon. But compound semiconductors nevertheless are pretty important. They are very strategic. You have silicon carbide, which is power, gallium arsenide, which is high frequency, low power, and gallium nitride, which I will talk about, which is high frequency, high power in the RF space and also power electronics. Apart from the fact that if there are LEDs in this room, it's most likely gallium nitride based. So the vision for 2027 is to see if we can have gallium nitride technology, manufacturing technology that's based on a device process flow that is developed indigenously. Yeah. So I'm from the Indian Institute of Science, and I couldn't help but recognize, given what we've done over the last 20 years, that creating a good university takes time. We all know that. So does self-reliance in technology. And this cannot be more true of semiconductor process manufacturing technology, where each generation is built on the previous one. I mean, you have to go, to get to 2 nanometers, you have to come all the way 180 nanometers and so on, 58, 28 and below, and I'm guessing the Tatas are going to be at 28 now. So what we did in IISc, so the vision for 2027, as 2047, like I was telling you, is that we need to have indigenous GaN manufacturing technology, because unless and until you've developed a generation, you will not be able to build subsequent generations and be ahead of the world. You will always be a follower when you get technology from outside. I understand that in the case of silicon, it is difficult. So at times you need to jumpstart it the way the Tatas are doing. But eventually I'm guessing that if they want the next generation technology, they'll have to develop it, or to go ahead of the world, do something on their own. The point is that we don't, and the vision I have at least, is that not only do we need to have our own indigenous device manufacturing technology, but there is an ecosystem here. An ecosystem on the one side where there are systems manufacturers who exert a pull on this device availability, and on the other side, there is a supply chain that is able to support this device manufacture. So that is my take-home message as far as Vision 2047 is concerned, and I hope that it will fall in place. But to get to that in 2047, we can't start from scratch. So actually at the Indian Institute of Science, it is 2025 now, this is where we are standing here today. We actually have put in place a cutting edge, low volume production foundry for gallium nitride called GIKI, which was funded by MITI. It is an incubator, and we have startups. So I'm the founder of a startup called Agnet Semiconductors, which now goes all the way from making the epi wafer to manufacturing the device to converting it into packaged products that we are now putting in the hands of Indian customers.
So in some ways, as far as semiconductor device manufacturing is concerned in the private sector, Agnet is probably, to the best of my knowledge, one of the first such companies in India. But to get to this place in 2025, we couldn't have started here. So all this effort went back to 2005, where ISC set up its clean room, and we installed the first gallium nitride reactor in the gallium nitride program that was started there with funding from DRDO. Actually, as I speak about gallium nitride and HEMS, given that this session is, DRDO is one of the main organizers, it feels like I'm preaching to the choir, right? So we've come a long way at Sense, going from 2005 to 2025 now, and we plan to keep going. Yeah? So even though Sense started in 2005, the vision goes back to 1998 when the ISC clean room was set up. I was not even a faculty member in Sense then. Actually, Navkant, who is on the dais here, was one of the pioneers. And the reason I put this up is that without the, by the way, I don't have very strong political affiliations. The fab was eventually dedicated to the nation by the Prime Minister in 2015. And it was big enough and important enough for the Prime Minister to come down and inaugurate it. But fact remains that without facilities like this, it would have been impossible to set up this low volume production foundry called Geeky and have a startup like Agnet, make devices and sell it. So as Madhusudan was saying sometime before, government support has been there, it has been crucial, and without government support, this could not have happened. Yeah. So the Sense clean room today, if you visit us, which is one of the biggest in India, actually academically it's the biggest in India. It's ISO certified, it's India's largest academic fab facility, and it's nationally accessible to all. And it is in this facility that we are developing the gallium nitride technology that I was talking about. So why GaN? Two of the most important threads that run today is the increase in consumption of energy in the form of electricity. So GaN enables that. So if you bought a compact, wireless charger for your cell phone, there's a very good chance that there is gallium nitride inside. The other big thread, the other big trend is that we are increasingly communicating wirelessly, cell phones. So in the 6G base stations, there is GaN inside. But even more importantly, when you talk of radars and such, both ground-based and airborne, there is gallium nitride in there, because of which it has very high strategic importance. And that is evidenced by the fact that it is an export controlled technology. So there is a ban on the export of GaN to India from many countries as we speak. So the combined RF and power device GaN market is about $4 to $5 billion. The systems market is about 10 to 20 times that. This is just GaN electronics, but if you include LEDs, this will be about $30 to $50 billion as we speak. And in addition to that, if you include the other compound semiconductors, you will start seeing the numbers. See, when you talk about silicon, you're always talking in hundreds of billions of dollars. Compound semi is growing, and you have now started talking in terms of companies where the revenue is inching close to $100 billion or so. So if you followed the compound semi news like I have been doing over the last many years, there has been quite a bit of consolidation in the last 2 to 3 years. So this is the latest news from about 2 days ago, where it said Skyworks and Qorvo, these are two of the biggest companies in the US, they have combined to create a $22 billion entity. Okay, this is big news. And then Macom acquired Wolfspeed. If you're in the GaN space, you will know that Cree and Wolfspeed were two of the initial biggest companies. Then Renesas acquired Transform, which was the poster child of GaN power. Infineon acquired GaN Systems, and then TSMC of all people gave up GaN power because they said they couldn't compete with China. The point here is that even in the compound semi space, technology is maturing. There is consolidation. Compound semi companies are getting bigger, more stable. So the longer you stay, the more difficult it will be to compete with them. And India needs to be a part of the mix. And to do that, you have to have your own indigenous manufacturing technology. So we started doing that in ISC. From 2005 to 2015, we set up this platform. This is an MOCVD reactor, which first started making material available consistently. And as we speak, actually, we have done some 4,000 runs on this reactor. And once consistent material became available, we realized that it's not just enough to make the wafers. We put together a team that went all the way from making the wafers to making devices, to packaging them, to integrating them in systems. And once we decided to do that, I apologize for that ugly looking black snake there, around 2015, we submitted a proposal to the Government of India to set up a low volume production foundry. Actually, this was a proposal to set up an entire greenfield fab in India. But then around 2021, right in the middle of COVID, MIT finally allowed or funded us to set up a low volume prototyping facility. It's called Geeky. It is now ready. It's up and running at the Indian Institute of Science. And this is a photograph of the foundry. Like I told you, I have a lot of pretty pictures. And on this foundry, we've gone all the way from making wafers. So we host the world's largest production scale reactor. So this is not R&D anymore, it's production. What you see on the far right is our first generation technology using what is called an air bridge. We are now into a second generation technology which is based on vias. For those who worked on gallium nitride technology, you will know what I mean. And this is what I mean when I say that we need to have our own indigenous production capability. So our second generation process, which involves about 15 mask modules and 220 unit process steps, which takes about 28.8 days to complete from wafer start to wafer finish. So I'm not talking like an academic faculty member now, I'm talking like a production engineer. So that is ready. So this is what we call a 0.5 micron technology, which is ready to go into production. We are working on 0.25 and then eventually we'll hit 0.125. By the way, some of this is also there in GATEC and it was also developed in DRDO some time back. And 2025 onwards, we'll be moving towards power GaN technology on 8-inch wafers. The top two are RF, going up to 8 gigahertz. So products such as these are getting manufactured in India and we are putting them, they are getting tested with customers as we speak. So as far as RF and power go, what you see on the left-hand side is the output power versus frequency curve. The dots show the various kinds of products that are already available in the market. The green rectangle shows the areas that we hope to cover in the next 2 to 3 years, going all the way up to 12 gigahertz and up to 350 watts, discretes, and eventually we'll move towards MMICs. As far as power goes, you will see the x-axis, it's low frequency. But we hope to be in that space where we can enable 650 volt devices for the emerging electric vehicle market. Okay. So towards 2047, how do I visualize GaN? GaN by itself will of course be there, but it has to be integrated with silicon. And even though Navkan said that, Moore's law is tapering off, it's still alive. Nevertheless, the silicon industry is trying to integrate silicon technology with compound semi and other technologies as we speak, including MEMS. So we foresee, and increasingly you start seeing products that are highly integrated with silicon. You can't just buy GaN dies anymore. They come in blocks, especially on the power front. So we foresee heterogeneous integration with silicon being a key technology that we will have to focus on. I'm almost done. So if you, for example, open an iPhone 6 and you go all the way down, you will see a gallium nitride die from Qorvo or Triquint that's packaged in the power amplifier, or a gallium arsenide die. So what do I mean by ecosystem creation? This is actually a figure that I like a lot. The image is from McKinsey. See, the semiconductor ecosystem, all said and done, is globally integrated. Okay, so in this case, you see if you go from equipment to materials to design, fabless, and so on, it is there all over the world. Okay, it's not just one country that controls it. Of course, there are some countries, for example, if you take IDM, it is the US, but a pure play foundry, it's Taiwan, right? So the same thing is true of GaN. So this is the ecosystem that I'm talking about, that the vision is will hopefully be present in India to a much larger extent than it is today. So if there is an STIC 1 year from now, given what I see in terms of the startups that are getting incubated at Geeky, Yule is going to put some of those logos on this startup. So we are hoping that there will be systems manufacturers, device manufacturers, and actually below substrate supply, chemicals manufacturers, listed companies that now want to come in and manufacture things like trimethyl gallium and trimethyl aluminum in India that was unheard of before. So this is my vision 2047 in the sense that we will have indigenous manufacturing that is immersed in a slightly larger indigenous ecosystem, without which I think we'll always be a step behind the leading edge in the world. So with that, I'll end. Thank you.
I think we are behind schedule, so we'll skip the questions and you can ask the questions during the break. So we can move to the next speaker.
Yes, sir. Thank you so much, sir, for a forward-looking talk. And your vision for this technology truly underscores the potential to lead compound semiconductor technology by 2047 along with silicon. To take the session forward, may I now request Shri Ashish Johari, Scientist DRDO, to kindly introduce our next speaker, Dr. Suraj Rengarajan, sir.
Thank you, ma'am, and good evening to all. It's my proud privilege to introduce Dr. Suraj. Dr. Suraj is Managing Director and Head, Semiconductor Products Group, Applied Materials in India. In his present role on SPG's strategic objectives, he focuses on planning and growing a customer-focused organization, growing local leadership talent, enabling collaboration across India and Asia regions. Dr. Suraj started his career in Applied Materials, St. Clara in 1997, where he held different roles ranging from process engineering, technology, program management, and product marketing. He moved to India in 2007 to head Sun Fab Group for Applied Materials in India. Later, he headed the engineering group for dielectric deposition. As the India CTO, he worked on material engineering driven inflections to develop and commercialize new technologies. Dr. Suraj holds a BTech degree from IIT Madras in metallurgical engineers and earned his MS and PhD from University of Texas in Austin in material science. He has over 15 US patents and holds more than 20 publications. With this, I now request Dr. Suraj to deliver his talk, please.
Thank you. Good afternoon. So first, I'd like to thank STEC 2025 for this opportunity. And I've been in many conferences. On the third day afternoon, having a full house is a big testament to the organizers. So big round of applause to the organizers for this, right? So let me get started. I think we've had a wide range of topics, software, fabless, gallium nitride, and I'll also talk about one more area which I believe is very important. I represent Applied Materials, which is the leading semiconductor and display equipment manufacturing company. So I'd like to also clear up one topic that came up in the previous discussion. Amitesh ji is sitting here and the Minister Vaishnav ji are fully aware of what is required to build an end-to-end startup designed to manufacturing and application semiconductor ecosystem. So they are well aware of all the needs and we work closely with them and they are coming up with policy enhancements that will address all these gaps. So all of you stay tuned. And I think one of the things I would also try to talk about when Professor Raghavan showed that sort of ecosystem landscape, all areas need to be built up for an ecosystem to be sustainable. So that's something the government is aware and working on. And I also have the privilege of talking after Professor Raghavan in many events and reiterating the same message. So today I will look at the semiconductor landscape from a slightly different perspective. So the first thing for all of you who are looking at semiconductors, the reason why we are all here, right? I think Dr. Kamath talked about the strategic importance. The other reason we are also looking at it is from a commercial importance. This is going to become a $1 trillion industry. That's one of the reasons, in addition to the strategic aspect that all of us need to be aware of. I am going to talk mostly on inflections that are happening and will continue to happen, and why should we all be aware of that? And then maybe at the end I'll talk a little bit about what we can do. So the first thing is everything is going 3D. So Professor Naukanbhat talked about Moore's law challenges and all that stuff, right? So the way to address a lot of the Moore's law challenges, which is the scaling in 2 dimension, is to go 3 dimension. So if you look at that picture, gate all around, backside, and the 3D RAM, everything is going 3D. And so now the driver, right? Why is all this happening? So no presentation anywhere can be complete without AI. So AI is the driver of this. So if you just add up all the different markets, the 20, 30 markets for all of these, it comes to about 16 trillion there. So reference India GDP is close to about 5 trillion. So this is huge opportunity, right? So one of the reasons for all of us, and everything listed there has India impact. The AI data centers is something that India is looking at. Edge, AI, IoT from an application perspective, EV is an industry we want to grow, and renewable is something that we want to increase. So, and all of these have semiconductor implications. Okay, now from what is driving a lot of this change and why should we move to advanced packaging? So before we come to advanced packaging, so one thing I'd like to talk about, packaging is how most countries grew. Almost every country you can think of, right? Japan, China, Taiwan, everything started with packaging chips, and that is how India is also starting. Of the 10 companies that have been approved by ISM, almost all of them are going to do conventional packaging. Now here we are going to talk about advanced packaging. So if you look at that graph, so there is a big blip in terms of what we need in terms of performance. So many of you use ChatGPT and different copilots and all that. Every time you do something in that, the power requirement, performance requirement is a big challenge, the data centers and all that. So there is about a 13x difference in power consumption between typing the same thing in ChatGPT versus a simple Google search, right? So there is a lot of pressure on hardware performance. So the die sizes are getting bigger. So if you look at the right-hand side, the size of the die is now as big as the reticle, which is what your lithography system can do, right? That's one of the things that is driving this. The 3 things that all this is going to do from a packaging perspective. First, on the left-hand side, how can you put more interconnects together and more of them, right? That's interconnect packaging, and I'll talk a little bit about hybrid bonding as one of the solutions to get there. The second in the middle is how can you use these bigger dies more effectively. So if you look at that wafer in the middle, there are these black spots on the side. That's where you're not effectively using the wafer, because dies are square, your wafer is round. So there is a geometric effect because of it. You're not using your wafer well for the dies. So making a rectangular panel is a better utilization. So that's one thing that is happening. And then die stacking, heterogeneous integration. How do you put the different aspects of your chip and package together so that you can put and get more in a 3D perspective. So the first part is the hybrid bonding. So on the top left-hand side, micro bumps. That's how conventional bonding is done. You take 2 interconnects and like a solder, you sort of stitch them together. There are issues with that. First, if you look at that graph, and if you want to get more input outputs and you want to get better energy and power efficiency, you need to be able to get to a point where you can do interconnect to interconnect, copper to copper. That is the hybrid bonding the industry is moving towards. So this is one of the big inflections that is happening now. All the different companies are looking at how to implement this. And one of the reasons I'm talking about all this is that the India semiconductor industry manufacturing is going to start with conventional packaging, but how can we put this on their roadmap so that they can build products that are competitive globally and also have this in their roadmap. This is a hybrid bonding solution that the industry is looking at. So basically, how can you take copper interconnect and then bond copper to copper? It requires a specific process flow, and it requires a tool set that you can then take one interconnect and then sort of treat the two interconnects, then bond them, anneal them, so that you can make a hybrid bonding that gives you the performance improvement that you need. So the next part, as I mentioned, is panel. So you have the 300 millimeter wafer that is round, and as I said, your dies become bigger. So the industry is now looking at how do I go to a rectangular panel. So this one shows about 510 by 515. So a rectangular panel in which you can put all these dies and then put a substrate underneath that can hold all this, and you get more of these dies in a package. So one of the inflections for that is the interposer. So in the past, people have used organic interposers, and now the trend is to go towards a glass interposer. Glass interposer has more strength, it has better mechanical stiffness, thermal expansion, and it can support this bigger package. So if you look at all of these things, there is lithography changes. So there is a direct write lithography that can come in for packaging, which will make that more commercially viable. There is deposition in these large area going from wafer to panels. There is testing, and then there is the glass interposer. So these are different trends that are happening in advanced packaging today. So now coming to what does all this mean for a ecosystem that is growing, right? If you look at the top line, if you have to have all of these, semiconductor is a very conservative industry. All these take time. So typically, I used to be part of the industry as was there in the introduction. When I was studying, they talked about aluminum to copper. And that took a long time. It took about 10 to 15 years because the industry works in stages. First, university does the R&D, then equipment players try to validate, then you then try to get the supplier ecosystem to develop, and then you commercialize. So that whole thing on the top takes about 10 years, 15 years for a new inflection to come. So how can the ecosystem work together? How can industry, government, academia, suppliers work together to compress this? So one of the needs for this sort of an inflection to come faster is that to happen. And so Applied is looking at this EPIC model. We have started one in Singapore where there is ability now for industry, academia, and suppliers to work together to shorten some of these inflections so that they can come to commercialization faster. So this is our packaging development center in Singapore, started in 2012 with IME and A-Star. So a lot of products have been launched, and this is one thing that the packaging companies that have now started in India can work with this. They are working with this center so that they can accelerate their path to R&D and commercialization. There is also test vehicle capability. So one of the things is if I come up with a new flow, where can I go and test it? So that is also available at this center for people to validate their different process flows. So from a summary perspective, there are big inflections. AI is driving all the need, but there are big inflections happening in the semiconductor space. Packaging is where India's semiconductor manufacturing is starting today. And I think most companies will have some sort of packaging demonstrated in the next 2-3 years. What I would like to see is a roadmap forward where they can catch up and then maybe leapfrog where the industry is in the advanced packaging roadmap. That is something that will be required to demonstrate performance without the high-end 2 nanometer and all that. This is one way to get performance without going leading edge. And all of this will require people in this room, right? Industry, academia, suppliers, and the ecosystem to work together and collaborate to make this happen. And that's what I had. And one observation, so when people told me you're traveling to Delhi in winter, and you will hear people cough every 10 seconds, without AI, I can tell you it's every 5 seconds.
I think again, in the interest of time, we'll skip the questions and we can move now to the panel discussion. Professor Bhatt. Huh? Mementos.
Yes. With this, we conclude session on electronics and semiconductor manufacturing. You're requested to please be seated because we have next segment of panel discussion. So, to conclude this thematic segment, may I now request our session chair, Dr. Sameer V. Kamath, to kindly facilitate our esteemed dignitaries. May I request, sir, to please felicitate our chairman of thematic committee, Professor Navakant Bhatt, sir. Sir, it is there. So please do the felicitation of keynote speaker, Dr. Bobby Mitra, sir. Sir, may I request to felicitate Shri G.S. Madhusudan, sir. So please, felicitation of Dr. Srinivasan Raghavana, sir. So please, a felicitation of Dr. Suraj Rangarajan, sir. Thank you so much, sir. We will take a moment to capture this memorable occasion. May I now request our dignitaries on dais to please come for a photograph. Meanwhile, may I request our distinguished DGs and thematic committee members to please come on stage for a photograph. I request dignitaries to be present there. Yes, ma'am. Committee members. Thank you so much, sir. Now, may I request all participants and audience members, please be seated as we proceed to our next segment of panel discussion. So, over to Agrim.
You're needed on stage. Thanks a lot, Shrita madam. Now it is time for a stimulating panel discussion on India's electronics and semiconductor manufacturing ecosystem. This panel brings together experts whose ideas will help chart India's path toward a strong and self-reliant semiconductor ecosystem. Ladies and gentlemen, please join us in welcoming our eminent panelists. The discussion will be moderated by Professor Navakant Bhatt, Dean Interdisciplinary Sciences Division, IISc Bengaluru, and Chairman of the Thematic Committee on Electronics and Semiconductor Manufacturing. Dr. Sameer V. Kamath,
Secretary DDR&D and Chairman DRDO. It is my honor to invite to the dais Srimati Suma Varghese, Director General, Microelectronic Devices, Computational Systems and Cyber Systems Cluster, DRDO. She is heading frontier labs in the areas of artificial intelligence, semiconductors, quantum technologies and cyber-related activities. Professor Udyan Ganguly, Professor at the Department of Electrical Engineering, IIT Bombay. He currently serves as the Professor in charge for IIT Bombay Center for Semiconductor Technologies, CEMIX. Shri Amitesh Kumar Sinha, CEO of India Semiconductor Mission, Ministry of Electronics and Information Technology, MIT. Dr. Vibhu Sharma, Chief Technology Officer, L&T Semiconductors and Technologies. Professor Bhatt, the proceedings are now yours, please. Thank you.
Hello. Yeah, I think this is good. Again, we are running very late, so I think we will have to shorten quite a bit here. But the way we will run this panel, we will start with an opening remark from each of the panelists. And after that, we will have a set of questions to the panelists. And then we will open up for the audience because we would also like to have some interaction with the audience. So just to set the stage, we have heard the importance of electronics and semiconductors. There is no need for me to reiterate that. But the hope through this panel discussion is that we would be able to brainstorm what are the opportunities and challenges thereof. And we have also got an esteemed panel, representing all the stakeholders. We have Dr. Suma Varghese, DG, DRDO, a very distinguished scientist at DRDO, and we have Dr. Vibhu Sharma, representing industry. He is CTO of L&T Semiconductor, an Indian semiconductor company at that. So I'm keeping the introduction of each of the panelists very brief, so pardon me on that. We have Shri Amitesh Sinha, who is representing the government. He is actually the CEO of India Semiconductor Mission and ably driving this mission over the last few years. And I think we will hear from him the government perspective. And of course, finally, we have Professor Udyan Ganguly representing academia, because we believe that academia is also going to play a very important role, both from the point of view of workforce skill development as well as R&D, which will feed into the industrial requirements. So that's the bigger context. So let's get started. I will first invite Suma Varghese. If you can please provide strategic perspective of electronics and semiconductor manufacturing ecosystem, and also briefly discuss various initiatives that are ongoing currently in DRDO related to ESM.
Yeah, firstly, good evening to all of you. Just to start with what exactly, I think our secretary has already brought out, from missile systems to flight controls to radars to jammers, lasers to any of the secure communication systems. I think defense is filled with semiconductors, and semiconductor is what drives the defense. We have both the variety of semiconductors that are required, the intrinsic semiconductors that are needed for all our applications, and which is the, I should say, the reliable workhorse. And we have the race horses, that is the compound semiconductors that fires a radar and laser systems, which is the need of the hour. So if we look at it, the most stress was given to the compound semiconductors in the defense sector, because the intrinsic semiconductors, the commercial world took it over, and we were using the quartz components for most of our intrinsic semiconductor requirements. But strategically, if you look at it, the compound semiconductors were the driving force, whether it was for defense or space, where we have the gas or a GaN technology, and also in terms of IR technologies for our both short and medium wave IR requirements, and the lasers. And today we are talking about, we have initiated programs for quantum materials, basic materials for quantum technologies, and to photonics, which would be the game changer when it comes to replacement of some of the electronic technologies what we have. And I should also bring out here that this is not an individual DRDO-driven aspects, but we are working with academia through our DIA COE centers, and we are also funding the startups and industries for taking it forward. But scaling up in compound semiconductors is the need of the hour. We see that there is a mix of both military and civil domain, as rightly brought out by Vasu also, about how it is impacting both the worlds. So there is a need for big industries to come forward, to have the bigger fabs that can make India a global supplier in these areas. This is what we have to do. And I should say here on this, in this forum, that we have put up the expression of interest for anybody who can buy the technology from us, and we will be able to handhold for taking it for bigger applications future.
Thank you. That was excellent summary of the current status from the strategic perspective. So let me turn on to Professor Udayan Ganguly. If you can please come in with the academic perspective and particularly indicate how Indian academia is currently contributing to the ecosystem of electronics and semiconductors.
Thank you, Navkant. So if you look at semiconductors and if you go to the Bay Area and you find out, go into any office and you see the number of Indians there, you will always be surprised that Indians have consistently contributed. A lot of them are alums from our top institutes. That fundamentally means that we have excellent talent. What has happened in the recent past, in the last few years, has been that the talent has gone from undergraduate talent to master's talent and PhD talent. And they have been enabled by very specific curriculum and lab development. So in the IC design space, there is this SMDP program which METI has put forward. And over the 3 generations it has run, it has really developed essentially semiconductor leadership. And today there are a lot of startups in the fabless domain. But hardware is very hard. And one of the ways that we have created the sort of platform has been through the centers of excellence in nanoelectronics. So the first 2 were pioneered at ISC and IIT Bombay. And from there, I think there has been a significant amount of hands-on technology development. There has been various collaborations with international companies, Applied Materials, Global Foundries, Intel's. Significant funding has come in. There has been a lot of partnerships with DRDO, ISRO. So I think that's happened. What going forward we have to see is that that's been top talent, that's been top research talent. The question is when it goes to manufacturing, it is talent at all levels, from technicians all the way to researchers. And the question is, can we be more inclusive in our ability to train people? Training is fundamental to apes. You know, monkeys also train their kids to use tools. The more sophisticated places you go to, the more sophisticated skills, the better should be your training environment. The other thing that is required now is that training must happen at scale. So I think that's where academia must very strongly contribute. And there are many programs now that are being conceived under ISM, under METI, and we want to take those things forward. But one last thing I want to talk about is that there must be a significant amount of ecosystem reporting, status checks. And I think that's something that MOE, through this DevSet committee, we are running. Hopefully in the next few years, we'll have ecosystem reports on talent development, and that will provide benchmarks for us to beat. Thank you, Navkant.
Thank you. So now let's move on to the government perspective. Shri Amitesh ji, so you are driving this whole unprecedented revolution through India Semiconductor Mission. So can you present to us the current narrative of ESM and how do you view it in the ecosystem in general?
Thank you. Government perspective is, I will start with Madhusudanji's comment that what is the role of EMS players in this whole story. So starting 2014-15 when the phase manufacturing plan was started, that was a kind of duty structure that enabled certain kind of manufacturing, and after that it was escalated, it was enhanced, that effort was enhanced by PLI. So production link incentive is introduced by METI, by other ministries, and government has roughly two brackets I will try to put in. 10 billion bracket by Ministry of Electronics, PLI for mobile, PLI for IT hardware and all other schemes, and 10 billion by other ministries for electric vehicle, for renewable energy, for drone, for white goods and all those things. After that, when this EMS structure was growing, then government thought that now add value down the line. And then we introduced a different component manufacturing scheme. So there was earlier version of those schemes. And then now government has introduced electronic component manufacturing scheme. It's a very big scheme again to have all those components below the assembly to add the value. And parallelly, government decided to run India Semiconductor Mission, which will add further value below the component level. So on that topic, Madhusudanji has clearly defined that what is the roadmap and how these things, semiconductor chips will feed to components and how components will feed to assembly. So when you have attained a scale in EMS, now it is percolating down to components, and now the components will start using semiconductor chips. So this is the journey which government is envisaging. Now coming to India Semiconductor Mission, we are considering this design, manufacturing and packaging, all the three verticals. This is a 76,000 crore Government of India program. And in that the component of design was small, and rightly pointed out by Madhusudanji and others also that the kind of effort or kind of push we need to give this fabulous ecosystem is less in ISM 1.0, because we started this journey and we thought that the startups will take some time, and that is actually happening also. We have approved 24 design startups and they are now growing, but they will take some time. Now this DLI scheme, which is in the current avatar, is going to further magnified to a different level, where a lot of learnings from DLI 1.0 will be incorporated, and it will become a very big program, much more bigger than the earlier one. And it will have different flavors also. In manufacturing, we have already approved 10 semiconductor projects, one of Tata Fab, and this Tata Fab is having 5 technology nodes from 110 nanometer. In fact, they are also doing 180 nanometers, so 180, 130, 110, 90, 55, 40 and 28 nanometer. So that range they are covering. And before that also we were having a manufacturing facility. So our government labs like DRDO, Sitar, Semiconductor Laboratory, so we were having these government setups. But now in commercial space, Tata Semiconductor Fab is the first commercial fab which is coming. Apart from Tata, we have also approved one silicon carbide fab of 6M that is setting up in Odisha. In addition, there is another company called RIR, approved by Odisha government. They are also setting a silicon carbide fab in Odisha. So fab and packaging both is integrated there. We have now certain commercial manufacturing plants also. CDIL is the oldest plant which was there in the commercial space. And again, with the help of ISM mission, 4 projects have started commercial production. So Keynes is one of them. Sahasra was again a company, memory packaging company, set up under SPEX scheme of METI. They have also started commercial chip packaging. And there are 2 other facilities also. So Tata pilot line also started from Vemigal shipping commercial chips. And Micron and CG Power are just way behind. Maybe next 2-3 months they will also start commercial chip selling. So this is the activity happening on the manufacturing front. So in ISM 2.01 will go, so first phase is The money is already committed, and we have approved 10 projects, and you may see some other coming in future. But ISM 2.0 will again magnify this, and it will try to set up a complete ecosystem below this design, manufacturing, and packaging. So equipment, chemical, gases, and materials, all these things will be supported. So one of the question was related to the equipment manufacturing. So government METI has earlier supported LAM research and applied material 2 projects, and those projects are really doing very good. And now the time has to come to scale up those things also.
Yeah. Thank you, Sri Amitesh ji. And now let's move on to the industry perspective, because at the end of the day, industry has to do things at scale. So Dr. Vibhu Sharma, if you can give the industry perspective and specifically, L&T Semiconductor and industry in general.
Yeah, so let me start with industry in general. So I have been hearing all these talks starting from the AI and everything. So I would like to take 2 minutes to walk you through the background of the semiconductor industry, because I feel it's very vital to learn from what has been tried in other places. So if you see how semiconductor industry started in US, it was primarily based on their technological innovation combined with the capital markets free spirits. When it came to Europe, so Europe had a bit of a decade later start, but they had a huge benefit of extremely strong industrial base and their scientific rigor. So no wonder you see some of the finest equipment companies and some of the power devices companies, they come from Europe. Now outside this Western hemisphere, when we look at semiconductor success in the Eastern hemisphere, so we have this classical 4 waves, with Japan starting with DRAM logic, the same concept taken by South Korea, add export orientation and the cost competitiveness to the mix. And Taiwan, what Taiwan did was quite innovative at that time. When everyone was having an in-house fab, here's someone coming to you to say that, you outsource the fab facility. And now the irony of the situation is that 90% greater capacity for sub-10 nanometer nodes is with TSMC. And most recently, China. The Chinese learning is a state-driven capacity and the capability building. So now if you see all these success examples, they have a common trait. Everyone is starting from its key competences, whether it's like a core technology, a free capital market spirits, followed by industrial base to a government policy. When it comes to India, although we have a late start, but there are great advantages in our favor. The demographics are in favor. One of the biggest sector which comes to my attention is an energy sector. Already India has close to 500 gigawatt kind of capacity today as we are speaking. And as we progress down 2047, the target for Viksit Bharat, that where we see the demand would quadruple. Now it's not like you are burning the coal to get to that energy, it's all about the clean energy. And in the clean energy is semiconductors is playing exactly the same role like what the diesel or the coal played in the conventional industry. So this is one of a very unique industry perspective I would like to bring to attention to the audience here, like what India could leverage upon. And now the second part of the discussion on the L&T. Now in L&T, we have a very strong system differentiated semiconductor. Although we are fabless, but we have a system design philosophy. Like you have to start from system to define the latent opportunities, to identify the white space, the high value, high margin opportunities. And if you look at the trends, what we see is digitalization, decarbonization, and dependability. The best example I would give you is of electrical vehicles, because that's where you have all these 3 trends playing into picture. You have the decarbonization trend, you have a digitization with all these autonomous features, and plus the dependability for reliability. Now what's happening? As these trends are rolling, your 2,000 moving mechanical parts in vehicles are getting under 50 with electric vehicles. So the mechanics are reducing. Now, if mechanics are reducing, the gain is happening. Your software line of code in electric vehicles is already of the order of 300 million software line of codes. So you see this transition is happening from an asset, a mechanical asset, to an intelligent asset. And that's what creating an opportunities, be it an energy efficient power consumption with wide band gap, be it the cyber physical computation, to enable all the sensor fusion, connectivity, and all these things. So these are the kind of the core focuses we are targeting in L&T with the 3 verticals: energy, mobility, industrial, and supported by the application modules, where we say that we also offer a complete stack of the software to create that differentiation what the market needs.
Thank you. So thanks for opening remarks. Now, in the interest of time, the next round, I would request you to keep it very brief, 2 minutes per panelist, if you can, please. So the question to you, Dr. Suma Varghese, is, we have seen DRDO's capabilities, even during the Operation Sindhus in, implementing indigenous systems and deploying. But often we are constrained by export control. And this is going to happen and maybe scale up the way the geopolitics is panning out. So what are your strategies to overcome it, and how do you, not just the compound semi, but even you need other chips as well. So do you have some strategy, and what are the key initiatives that you would take from DRDO perspective in the next decade or so?
We have seen, as rightly brought out, even in the compound semi also, we have to scale up. That is what is one of the requirement based on what we have seen. But also in the intrinsic semiconductors, we are depending on the ISM mission that is happening in the country. And we are looking at some of the dedicated chips which are needed for trustworthy communications and trust-related aspects to be coming from the country. And thanks to ISM mission, they are taking up in a big way. Though it is up to 28 nanometer, I think from the point of reliability and trustworthiness, I think it is still a good option for us to go ahead and start there before we get on to the smaller nodes. And vertical stacking up is already being talked about. I think that would be the other driving factor, what we will be looking from academia who can work with us in how to vertically stack up for our future requirements.
Thank you. So, Professor Ganguly, if you look at the pace at which the semiconductor technology is progressing, the curriculum has to also evolve at a very fast pace. This is a real challenge, because often our curriculum gets stagnated in past century sometimes, right? So how do you address the challenge in the context of semiconductor technology, and also how do you bring in the collaboration with the other ecosystem, be it strategic sector or industry? Only when you work together you can really make the curriculum current and also R&D current.
Yeah. So Navkan, I think very, very good question. So the space at which things move, right? I personally think that things will keep moving. The question is, do our students know how to solve problems? And the nature of problem solving depends upon putting somebody in a new space and seeing how they respond. So that is one part of it. The second part of it, and that's something IITs have done very well. I see the top institutes. Relevant training requires sort of looking at having classrooms which have the right content, the right labs, educational labs with around semiconductors is, I think, very critical. Most companies require Indian engineers who are cheap by 2x cheaper, but also very good. You cannot say, I'm going to give you something which is substandard and cost and low cost. That doesn't work. So for us, it has to be very high quality engineers, but cost of living here is lower, and that's where we make up our difference. So very good labs, that is very important, but labs are expensive. So what's very important for us is to funnel talent which is across the country into these labs in a very effective manner. Most of our higher education institutes are based on good filtering. One of the things that we can do is use online courses which are scalable and use those as filters. The last comment you had was industry, academia, DRDO. I think a lot of DIACOE, that bunch of things. I think if we can create an IMEC like R&D center, or use IMECs or TSRIs and other places, I think those sort of renting capabilities which are close to industry, short-term goal, bringing up an IMEC like R&D center in India, a mid-term goal. I think that's the answer.
Great, yeah. Shri Amitesh ji, you mentioned about ISM 2.0. It's so heartening to hear that, because in semiconductors, the government support has to be sustained for many years. I mean, even US has a very mature ecosystem, but you see the way government is supporting. So I'm just wondering, what are your thoughts about ISM 2.0, 3.0, or what have you going forward? And also, what are your expectations from the ecosystem when you are doing this?
You have heard Honorable Prime Minister speaking during Semicon 2025. So he clearly hinted that there is a long-term vision of sustaining this semiconductor effort, and that is giving us all hope and direction to work on Semicon 2.0. So Semicon 2.0 will be much more comprehensive than Semicon 1.0. We have targeted design, manufacturing and packaging here. So we will continue that, and we will go down that particular support system, where chemical, gases, materials, equipment manufacturing, even R&D, starting R&D in technology nodes and advanced packaging will be the key focus area. So we fully understand that the design is our forte, and design capability will lead us to fabless ecosystem also, and in advanced packaging also. So these two things will be our key focus area, and we will continue our journey in technology nodes on the lower side in form of attracting new companies and also doing some R&D in that area. So this is our goal, and right now we are working on that. Until the program is approved, we cannot say that what is the final blueprint, but we will work on this, setting up a complete ecosystem so that the 110 billion demand of semiconductors by 2030, which will be 10 to 11% of the global demand. So we will be, a large portion of that can be met by the Indian fab and fabless companies, including the packaging. So packaging will be the first area which will give us a leadership role, and soon we will migrate to advanced packaging from packaging. And design is the big thing that we are eyeing, and since we have all design engineers working in all good companies, we expect that whether the Indian design company like L&T sitting here or the startups, they become a good design company going forward.
Thank you. So, Dr. Vibhu Sharma, eventually the semiconductor chips have to be used in certain systems, right? So, what are the new emerging application domains that you see from industry perspective in the next decade or so? And also the other related question is, there has to be a balance between the startup and established industries, right? Because established industry are risk averse, startup have a lot of risk appetite, So how do you see that balance, and is there any intervention required in the ecosystem?
Second is a tough question, so I will start with the first one. See, in terms of the trends, like the trends now, especially we are talking about post-COVID, mid of the 2020 decade, we see the multidimensional forces in action. Like at the first dimension, let's talk about what are the pure mega trends which are emerging, which I already talked in my previous answer. Digitization, AI workloads, like wherever you go, everyone talks about AI. The AI infrastructure is demanding a new kind of power conversion. Like no one imagined like DC lines, HVDC getting into the data centers, vertical power delivery. So data center itself has emerged a kind of industry which is dictating new generation of chips, not only on the AI computation side, but on the power delivery, on connectivity side. Then other emerging application which comes to the top of our attention is now in the area of robotics. Which many people say, or what we are observing is a right manifestation of the future of AI as a physical AI. And even if I take a prototype today of a robot, a decent robot, it could be moving, let's say, a dog, which you popularly have seen videos on social media. The average semiconductor content is already $2,500. And we are not talking about yet that robot which has met all the safety standards with a nice interfaces. It's only going to go up. That's another major second trend we see. The third kind of trend is purely a technology push, where like the Moore's law is not dying. It's just that the race for more scale technology nodes is also being shared by the advances in better performance through chiplets, through data transfer via silicon photonics, through wide bandgap devices. So if you now see all these mixes and take the geopolitics into account, like the CHIPS Act and localization of supply chain, these are creating a lot of opportunities and are going to define a next generation winners in this semiconductor race?
Okay, thank you. I've been told by the organizer that we need to wrap up in 2 minutes. So just 1 or 2 questions from the audience. Otherwise, it would look bad if we don't get any questions from the audience. Yeah, there is a question here. I'm sorry, we can't allow many questions. I'm told that minister has already come and we need to wrap up this session. I'll keep my concluding remarks short. So, yeah, go ahead. Yeah.
Yeah, so I would like to ask a question about thermal interface materials for the electronic packaging, because heat management is the key issue there, because we are getting into CPU and GPUs, and when you start using AI, so the heat dissipation will be more and more. So I'm just wondering, because when we did a survey on what kind of thermal grease and films are there, most of the stuff what we use today are Chinese made. We don't have any indigenous thermal solutions in India. I'm just wondering, that's 20% of the cost of a laptop comes from the thermal solutions as the
So can you please brief? Your question is what are we doing for thermal management?
Exactly, electronics.
So anybody want, Vibhu, you want to take up that question, or Udayan? Anybody? Yeah.
So there are a bunch of research programs going on under DST, under METI, and also certain large packaging programs will include this sort of research. So I think it is an important question, and there needs to be some significant acceleration in answering this question.
Any other questions or points?
I will just add one thing. Yeah. There will be a dedicated center for addressing thermal problems.
Excellent. So, yeah. So, yeah.
I have a question.
Yeah.
So, first of all, thank you for your insights. My question is in terms of talent, and more importantly, vocational talent, technicians on operators, how can a private player or a startup help the ecosystem? Or does the AI and automation make the need not viable?
So, your question is whether AI and automation... No, actually, so most fabs hire talent from organizations which do specific operator and technician training. In India, that needs to ramp up. And I think the opportunities need to be sort of discussed. I think there's more details, but there are also models abroad. So I think I'll request you to look at those. Thank you.
Okay. Thank you. I think we one last question and we will close after that.
Yeah. Sir, very good evening. It's a wonderful sessions. I'm coming from the Industrial University, Gujarat, and as you asked one question to Professor Ganguly about curriculum, the AICT made one curriculum, model curriculum, and UGC, now AICT and UGC both are there, and I would like to know the role of METI and ISM in joining to framing a curriculum, because physics, chemistry and material are keeping out and people are running beyond electronics, electronic communication, forgetting semiconductor manufacturing and that we have side design.
Yeah, thank you. Get the point. So integration across different ministries, AICT, and there's already an AICT initiative. Yeah, go ahead. Yeah.
I think that there is already an AICT curriculum that has been developed. I think METI will not worry if AICT does the job. So let AICT do what needs to be done. But I think the integration between materials and others, it can be further refined, is my comment. Yeah.
Okay, so
can I add one liner on this? Yeah. In my experience, what's a gap I'm observing is too much focus is also dangerous when it comes to education. You rightly said about only communication or a particular course. What the future engineers need to succeed in the semiconductor race is a strong interdisciplinary knowledge. So I would support your plan.
Yeah. So that's a very important point, and I'm very sorry we are rushing this panel, but let's conclude now. As I said, I will be very brief. I think, as you heard from all the panelists, I think the future directions look extremely promising, both on talent development, government policies, the way strategic sector is positioning itself for building the ecosystem, and of course industry coming in and pitching in terms of the collaboration. So I think we will end this panel with this positive note. Thank you for joining us.
We come to end of the session, and I thank the session chair, Dr. Kamath, and I thank all the speakers and all the audience. With that, we are keeping it very brief, and we are skipping some of the things because Minister has already arrived. Kindly proceed to the plenary hall that is at floor number 3. And felicitation, we are just doing unofficially here. Everyone can please proceed. That is the message. That is the message we got.